titles are wrong, scratch it out and put at least a shorthand for the title that you're looking at. So the first one should have been the night vision, and the second one is the microwave backhaul. And then just write that down quickly if you do not have the correct score sheet right now. All right, and so our next talk is, our next presentation is on time synchronization for wireless transceivers. You may begin.
Well, as he just said, our project is time synchronization for wireless transceivers with UTDesign team. My name is Jeff Ramsey. I was part of the ultrasound, and fortunately, because of time constraints, I won't be able to talk much about that unless you ask a question from my closing session. This is Brad Duke. He was in charge of the microcontrollers, and this is Sue Lee. He was responsible for helping us collect and test some of the various RF transmitter receivers in ultrasound. And basically, for our project, we designed and implemented two methods to wirelessly synchronize two separate microcontrollers using radio frequency beams. And to synchronize, what that basically means is we want these two separate microcontrollers, these little computers, to be operating on the same time so that we can have a common time reference from which to do calculations based on. And our application was the ultrasound distance finder using the time flight principle. And the main problem our project addresses is the synchronization error, basically the difference in the received time reference from these two microcontrollers. And that basically, depending on your synchronization error, is ultimately going to introduce either a little bit of error into in our case, the distance measurements, or a lot of error. And so, talking about our methods, method one here, focusing mainly on the synchronization and how that was done. Method one here involves a separate RF transmitter, which transmits its own synchronizing beam to the microcontrollers, and then both of these microcontrollers have the same model of radio frequency receiver on it. So ideally, they'll receive the synchronization beam at the same time and be operating on the same time. You see there at T2, it's ideally they receive it at the same time. Going on to method two, we have one RF transmitter and one RF receiver. The first microcontroller transmits signals the beam to be sent to the second one, which picks it up and it's received at time two, which is the average time over a large set of trials. And that's going to be a constant for the receiver, is the average. And the synchronization error for that one is going to be each individual received time minus the average time. And for the first one, it's going to be the two individual received times, alpha 1 minus alpha 2. And here are our results here. The top left graph you see had a variance in the over 600 trials of about 35 milliseconds, standard deviation of 0.188, and max synchronization error that we measured at 1.106 microseconds. The second one had a max error of 2.455 microseconds with a variance of 0.024. What the variance means is how consistent are these data points, how close are they to the average. And since they have a really small variance, that means that not something we chose, it's something we thought would be